In the dim light of a Philadelphia mill, Oliver Evans watched grain transform into flour with machines that moved like clockwork. A century later, his idea of using vapor pressure to make ice found a new form in a patent for refrigeration. Meanwhile, in the 1840s, William Thomson calculated a temperature so cold it seemed almost mythical. Stephen Crane, in 1897, wrote of nature's unyielding rules, and before him, William Cullen had already glimpsed the science of cold. The lecture is about to begin. The air smells of wood and damp earth, a coolness that isn't quite the chill of winter, but a deeper, steadier absence of warmth. Sunlight filters through cracks in the wooden walls, illuminating dust motes dancing in the still air. It's the smell of preservation, of time held back. This is an ice house, one of the last bastions of a world before reliable power, before the quiet hum that now fills so many kitchens. We call it refrigeration, the artificial cooling of a space, but for a long time it wasn't artificial at all. It was simply a careful negotiation with the seasons, a storing of winter's gift against the heat of summer. Hold that image for a moment, the weight of the wooden door, the rough-hewn planks, the straw packed into the walls as insulation. A place built not to make cold, but to keep it, to hold on to something fleeting, something that would otherwise vanish. And in that holding, a story begins, a story of wanting to slow the inevitable, to push back against decay, to taste summer in the heart of winter. For centuries, that pushback came in the form of ice, harvested from frozen lakes and ponds, packed deep in straw and sawdust. This ice was a commodity more precious than gold. It traveled across continents, a fragile cargo shipped in insulated holds, melting slowly on its journey to supply the tables of the wealthy and the needs of preserving food. It was a logistical marvel, a delicate balance of timing and resources, and it was ultimately limited, dependent on the whims of the weather, vulnerable to the relentless advance of warmth. The desire for something more reliable, something self-sustaining, began to stir in the late 18th and early 19th centuries. It wasn't a single moment of revelation, but a gradual accumulation of curiosity, a series of experiments driven by the same human impulse that built this very ice house, the desire to control our environment. One name appears prominently in those early records, rooted commercially in Philadelphia, a city already a hub of innovation and trade. Oliver Evans, born in Newport, Delaware, received little formal education, apprenticed to a wheelwright in his mid-teens, and yet he became one of the first Americans to build steam engines. He wasn't interested in steam for its own sake, not in the way that some of his contemporaries were fascinated by its power. He saw steam as a tool, a means to automate processes, to create systems that worked without constant human intervention. He built the first fully automated flour mill, a complex arrangement of bucket chains and conveyor belts that could grind grain, sift the flour, and even bag the finished product with minimal human input. It was a revolutionary concept, a glimpse into a future where machines would take on the burden of labor. And it was this same drive for automation that led him to explore the possibilities of refrigeration. Evans was an advocate of high-pressure steam, a technology that was still considered risky and experimental at the time. He believed that high-pressure steam engines were more efficient and more powerful than their low-pressure counterparts, and in 1805 he patented a vapor compression refrigeration machine. It wasn't the elegant, self-contained unit we know today, not by a long shot. It was a crude apparatus, a series of tanks and pumps powered by a steam engine, designed to create ice by evaporating ether under pressure. The process, in its simplest form, involved taking a liquid, in this case ether, and forcing it to evaporate. Evaporation is a cooling process because it requires energy. When a liquid changes into a gas, it absorbs heat from its surroundings. Evans's machine used this principle to cool a chamber, creating a small amount of ice. It was a proof of concept, a demonstration that artificial refrigeration was possible. It's important to understand that this wasn't about creating a comfortable temperature for storing food, not yet. It was about creating a process, a repeatable method for producing ice on demand. The machine was bulky, expensive, and unreliable, but it laid the groundwork for future developments. It showed that thermal energy could be transferred against its natural gradient, that heat could be moved from one place to another, even from a colder place to a warmer one. Think of it like this. Imagine a room with a hot corner and a cold corner. Normally, heat flows from the hot corner to the cold corner until both corners reach the same temperature. Evans's machine was an attempt to reverse that process, to force heat to flow from the cold corner to the hot corner. And to do that, it required energy in the form of steam power. The refrigerant, the substance that absorbs and releases heat, is the key to this process. In Evans's machine, it was ether. Modern refrigerators use a variety of different refrigerants, each with its own properties and advantages. But the principle remains the same. The refrigerant absorbs heat from the inside of the refrigerator, changing from a liquid to a gas, and then releases that heat to the outside, changing back into a liquid. It's a continuous cycle, a closed loop, where heat is constantly being moved from one place to another. The ice house, of course, didn't use a refrigerant in the same way. It relied on the ice itself to absorb heat as it melted. It was a passive system, dependent on the existing cold of winter. Evans's machine was active, a self-sustaining heat exchanger that could create cold even in the middle of summer. But it wasn't immediately successful. The technology was too expensive, too complex, and too unreliable to compete with the established ice trade. And crucially, it required a constant supply of steam power, which was also expensive and unreliable. The idea, however, had been planted. The seed of artificial refrigeration had been sown. For decades, the ice trade continued to dominate. But as steam engine technology improved, and as the demand for refrigeration grew, the idea of a mechanical ice-making machine began to gain traction. It wouldn't be Evans who perfected it, not directly. But his work, his relentless pursuit of automation, his understanding of the fundamental principles of heat transfer paved the way for the breakthroughs that would come. The optimal temperature range for perishable food storage, we now know, is between 3 and 5 degrees Celsius, 37 to 41 degrees Fahrenheit. Below that, water freezes, damaging the cellular structure of the food. Above that, bacteria reproduce rapidly, leading to spoilage. Refrigerators maintain a temperature a few degrees above the freezing point of water, creating an environment where bacterial growth is slowed but not stopped entirely. It's a delicate balance, a constant struggle against the forces of decay. And the ice house, for all its limitations, was a testament to that same struggle. A place built to hold back time, to preserve the bounty of the harvest, to savor the sweetness of summer long after the leaves had fallen. It was a temporary reprieve, a fragile victory against the inevitable, but it was a victory nonetheless. A quiet acknowledgement of our desire to control our environment, to shape the world around us, to slow the relentless march of time. The wooden walls still hold the scent of damp earth and wood, a coolness that isn't quite the chill of winter, but a deeper, steadier absence of warmth. It's a reminder that the technologies we take for granted today were once radical innovations, born from a simple desire to preserve what we value. A desire that continues to drive us, even now, to explore the boundaries of what is possible. And the understanding that even as we strive to control the environment, we are always subject to its laws, its inherent tendencies, the laws that govern the flow of heat, the reproduction of bacteria, and the inevitable passage of time. The air in the engine room is thick with the smell of oil and coal smoke, a metallic tang overlaid with the sweetness of escaping steam. Sunlight, fractured by grimy panes, casts long shadows across the polished brass of the valves and the iron skin of the cylinders. It's a restless place, a constant rhythm of pistons and gears, a mechanical lung breathing in fire and exhaling power. We spoke last time of holding back time, of the ice house as a fortress against the inevitable, but the engine room doesn't hold. It does. It doesn't resist decay, it overcomes it by a different means altogether. It's a subtle shift in perspective, and one that requires a deeper understanding of what we mean when we talk about cold, or heat, or even, fundamentally, energy. The simple image of moving heat, of taking it from one place to another, is a useful starting point, but it quickly runs into trouble. It suggests a tidy, directional flow, a clear separation between what is hot and what is cold, but the universe doesn't quite work that way. It's not a simple matter of relocation. It's a question of probability, of the countless tiny motions of atoms and molecules, and of the relentless tendency toward what is most likely. Consider for a moment a single molecule of water bouncing around within a glass. It's not a still life. It's a whirlwind of activity, colliding with its neighbors, absorbing energy from them and passing it along. Some molecules move faster than others, possess more kinetic energy. We experience this average kinetic energy as temperature. If you were to isolate that single molecule, it wouldn't have a temperature. Temperature is a property of the whole, a collective measurement, and if you were to observe it for long enough, you'd see it sometimes slow down, sometimes speed up, a constant dance of exchange. Now imagine two glasses, one filled with warm water, the other with cold. If you bring them close, molecules from the warmer glass will inevitably begin to drift into the colder one, carrying their energy with them. It's not a conscious decision on the part of the molecules, of course. It's simply a matter of chance, of the random walk of particles. There are more ways for energy to be distributed evenly than for it to remain concentrated in one place, and given enough time, it will happen. This is the essence of the second law of thermodynamics. Heat flows spontaneously from hotter to colder regions. This law is not a prohibition, not a rule that can be broken. It's a statement of probability, a reflection of the fundamental asymmetry of the universe. You can certainly force heat to flow from cold to hot, but it will always require an input of energy, a deliberate intervention to overcome the natural tendency toward equilibrium. And that intervention, that expenditure of energy, is precisely what a refrigeration machine does. The engine, then, is not defying the second law. It is enacting it, but in a controlled and purposeful way. It's not creating cold, but concentrating cold by moving heat elsewhere. But the question remains, where does that heat go, and how much energy does it take to move it? William Thomson, later Lord Kelvin, spent much of his life grappling with these questions. He was, for 53 years, a professor at the University of Glasgow, a tireless investigator of the properties of heat and energy. It was he who, in the mid-19th century, formulated the concept of absolute zero, the theoretical point at which all molecular motion ceases. He determined it to be approximately 273.15 degrees C or 459.67 dgF. This wasn't merely a mathematical abstraction, it was a fundamental limit, a lower bound on temperature itself. You can cool something to 200 degrees or even 260 degrees, but you can never reach absolute zero. The reason is simple. To remove the last vestiges of heat, you would need to extract energy from the system without introducing any disturbance at all. But any measurement, any intervention, inevitably introduces energy, however small. The very act of observing a system changes it. This is not a limitation of our instruments, but a fundamental property of the universe. The more precisely you try to measure something, the more you disturb it. Think of trying to detect a single dust mote in a room. You could shine a light on it, but the light itself will exert a force, nudging the mote out of place. You could use a delicate sensor, but the sensor will also interact with the mote, altering its motion. The more sensitive your detector, the more profound the disturbance. Kelvin understood this intimately. He recognized that there was a ceiling on every channel of energy transfer, a limit to how efficiently heat could be moved, how effectively work could be done. It wasn't a matter of finding a better engine or a more efficient refrigerant. It was a matter of the fundamental laws of physics. The engine room, then, is a place of diminishing returns. With each improvement in design, with each refinement of technique, the gains become smaller and smaller. You can extract more and more heat, concentrate more and more cold, but you will never achieve perfect efficiency. There will always be losses, always be a residue of energy that cannot be captured, always be a limit to what is possible. This isn't a cause for despair, but a source of wonder. It reveals the inherent complexity of the universe, the subtle interplay of forces that govern all things. The engine, in its tireless pursuit of cold, is not merely a machine. It's a testament to the ingenuity of human endeavor and a humbling reminder of the limits of our knowledge. And it's here, in this acknowledgement of limits, that a curious connection emerges, a resonance with the world of literature. In 1897, Stephen Crane published The Open Boat, a stark and unforgiving novella about 4 men adrift in a small dinghy after a shipwreck. The story is a masterclass in realism, a relentless portrayal of human struggle against the indifference of nature. But beneath the surface of the narrative lies a deeper, more profound theme, the struggle against entropy, the inevitable decay of order. The men are battling not just the waves and the cold, but the relentless march of time, the gradual disintegration of hope. They understand instinctively that their efforts are ultimately futile, that the universe is indifferent to their fate. The story is not about survival, but about the dignity of struggle in the face of inevitable defeat. The connection to thermodynamics is not accidental. Crane, though not a scientist, was deeply attuned to the underlying currents of the physical world. He understood that life is a constant battle against entropy, a relentless expenditure of energy to maintain order in a universe that is constantly tending toward chaos. The open boat, like the engine room, is a place of diminishing returns, a desperate attempt to hold back the inevitable. But even in defeat, there is a kind of beauty, a quiet resilience that transcends the limitations of the physical world. The men in the boat, despite their exhaustion and despair, continue to row, to bail, to fight for survival. They understand that their efforts may be futile, but they refuse to surrender. This is the essence of the human spirit, the ability to find meaning and purpose in the face of inevitable decay. The engine, then, and the open boat are both metaphors for the same fundamental truth, that life is a constant battle against entropy, a relentless expenditure of energy to maintain order in a universe that is constantly tending toward chaos. And in that battle, the very act of striving, of refusing to surrender, is a victory in itself. The steam hisses, the gears grind, the pistons pump. The engine continues its tireless work, moving heat from one place to another, concentrating cold, defying the inevitable. But even as it does so, it acknowledges the limits of its power, the fundamental laws of physics that govern all things. It's a dance of precision and chaos, a testament to the ingenuity of human endeavor, and a humbling reminder of the vastness and complexity of the universe. The machine is not merely cooling something, it is holding a mirror to the fundamental processes of existence, revealing the underlying order and disorder that shape our world. And what this means, ultimately, is that every act of preservation, every attempt to slow decay, is a temporary victory, a fleeting moment of order in a universe that is constantly tending toward chaos. It is a fight we will never win, but it is a fight worth fighting nonetheless. The air in this room is cool, but not the aggressive chill of a modern freezer. It's the coolness of metal, of something holding itself back from warmth, a deliberate resistance. This machine, a relic of early refrigeration, occupies a surprising amount of space. Polished copper coils snake across a dark wooden frame, rising to a bulbous glass condenser, faintly clouded with the residue of countless experiments. It's a complex arrangement far removed from the sleek simplicity of the boxes we know today. The scent here isn't sterile. It's faintly sweet, a hint of ether and the metallic tang of worked brass. You can almost feel the weight of the questions it once held. The slow, methodical pursuit of a colder world. William Cullen, a physician and chemist teaching at the University of Glasgow, first demonstrated artificial refrigeration in 1748. It wasn't a machine intended to preserve food, not at first. It was an exercise in pure scientific curiosity, a way to distill spirits more efficiently. He understood that evaporation drew heat from its surroundings, and he sought to harness this principle. He didn't see cold as a thing to be created, but as a consequence of removing warmth. The device itself was deceptively simple. A pump created a partial vacuum over ethyl ether, allowing it to boil at a much lower temperature than usual. As the ether vaporized, it absorbed heat from the surrounding air, chilling everything nearby. It was a fleeting chill, a parlor trick more than a practical invention. But it was enough to prove the possibility, to plant the seed of an idea that would take root and blossom over the next century. The machine before us isn't Cullen's original apparatus, of course. It's a later refinement, built decades after his initial demonstration, but it shares the same core principle. Look closely at the coils. The liquid inside, likely ether, though other solvents were experimented with, is constantly circulating. The pump, driven by a hand crank, lowers the pressure, encouraging the liquid to evaporate. This isn't a smooth, continuous process. It's a series of small, controlled explosions of vapor, each one stealing a tiny amount of heat from the air. The glass condenser, perched above the coils, is where the vapor is cooled and condensed back into a liquid, ready to repeat the cycle. Notice the fine droplets of condensation clinging to the glass. They form slowly, then coalesce into larger beads, tracing paths down the curved surface. It's a visible record of the heat being removed, a testament to the machine's tireless effort. The problem, as always, was scale. Cullen's demonstration was small, localized. Maintaining a sustained, significant chill required a constant input of energy, and the process was inherently inefficient. It was a curiosity, a laboratory tool, but not a practical solution for preserving food or cooling larger spaces. The idea lingered, though, resurfacing in various forms throughout the 18th and early 19th centuries. Oliver Evans, an American inventor, sketched designs for a vapor compression refrigeration machine in 1805, but he never built a working model. The science was there, but the engineering wasn't quite ready. It was Jacob Perkins, born in Newburyport, Massachusetts in 1766, who truly brought the vapor compression cycle to life. He was a man of restless ingenuity, apprenticed to a goldsmith but driven by a fascination with mechanics and physics. He held 21 American and 19 English patents, covering a vast range of inventions, from steel engraving to precision clocks. He arrived in London in 1819, seeking to capitalize on his ideas and find a market for his inventions. He was elected a Fellow of the American Academy of Arts and Sciences in 1813 and a member of the American Philosophical Society in 1819, recognition of his wide-ranging intellect. Perkins wasn't motivated by a single grand vision. He was a problem solver, constantly seeking ways to improve existing technologies, and he saw the potential in refrigeration, not as a means of creating cold, but as a way to create a reliable, predictable industrial process. The machine before us, or one very much like it, is the direct result of his work. He received his first patent for vapor compression refrigeration on August 14, 1834. It wasn't a radical departure from Cullen's original concept, but it was a significant refinement. Perkins understood that the key to efficiency lay in controlling the flow of the refrigerant and maximizing the surface area for heat exchange. He used ether as his working fluid, but he also experimented with other substances, searching for one with optimal thermodynamic properties. Imagine the process unfolding within the coils. The ether, pumped into a sealed chamber, is compressed. This isn't a gentle squeezing, it's a forceful reduction in volume, increasing the pressure and consequently the temperature of the liquid. It's a strange state, a liquid heated by compression, poised on the edge of transformation. The compressed ether is then forced through a series of coils, exposed to the surrounding air. As it expands, it absorbs heat, cooling down rapidly. This isn't a passive process, it's a violent release of energy, a sudden drop in pressure that drives the cooling effect. The vaporized ether then flows into the condenser, where it's cooled and condensed back into a liquid, ready to begin the cycle anew. The entire process is a carefully orchestrated dance of pressure and temperature, a constant struggle against the second law of thermodynamics. The condenser itself is a marvel of engineering. The glass bulb is surrounded by a cooling jacket filled with water. The water absorbs the heat released by the condensing ether, keeping the temperature low enough for the vapor to return to its liquid state. The water, in turn, is circulated through a separate cooling system, often using a natural source of cold water, a stream, a well, or a spring. It's a closed loop, a self-contained system that requires a constant input of energy to maintain its equilibrium. Perkins's design was remarkably robust, capable of producing a sustained chill for hours, even days. He envisioned using it for a variety of applications: brewing beer, distilling spirits, and most importantly, preserving food. The machine wasn't an immediate success. It was expensive, complex, and required skilled operators to maintain. It wasn't a simple plug-and-play device. But it laid the groundwork for the refrigeration industry that would emerge in the late 19th and early 20th centuries. Perkins partnered with Angier March Perkins in 1829–30, forming a company to manufacture and market his inventions. They built several machines, primarily for industrial applications, but the market remained limited. The technology was ahead of its time, hampered by the lack of a widespread infrastructure for electricity and the relatively high cost of manufacturing. Decades later, in 1915, Alfred Mellowes, an electrical engineer from Dayton, Ohio, took a different approach. He wasn't interested in building large-scale industrial machines. He wanted to create a refrigerator for the home. He recognized that the key to widespread adoption was simplicity and convenience. He patented the first self-contained electric refrigerator in Fort Wayne, Indiana, a compact unit that could be plugged into a standard electrical outlet. He founded the Guardian Refrigerator Company in 1916, partnering with J.W. Murray to manufacture and sell his refrigerators. Mellowes's refrigerator wasn't a radical departure from Perkins's design, but it was a significant simplification. He used a hermetically sealed compressor, eliminating the need for a separate pump and reducing the risk of leaks. He also used a more efficient refrigerant, a mixture of ammonia and water, and a more effective insulation system. The result was a compact, reliable, and relatively affordable refrigerator that quickly gained popularity. Look at the way the machine before us is constructed. The copper coils are carefully arranged to maximize heat exchange. The glass condenser is sealed to prevent leaks, and the entire unit is insulated to minimize heat gain. It's a testament to the ingenuity of the engineers who designed it, a product of decades of experimentation and refinement. The machine isn't just a collection of metal and glass, it's a symbol of human ambition, a relentless pursuit of control over the natural world. What this means is that the story of cold isn't a linear progression, a simple march of technological advancement. It's a series of incremental improvements, each one building on the work of those who came before. Cullen provided the initial spark, Perkins refined the process, and Mellowes brought it to the masses. Each inventor faced unique challenges, each one pushing the boundaries of what was possible. And each one left their mark on the world, shaping the way we live and the way we interact with the environment. The chill in this room, then, isn't just a consequence of physics. It's a legacy of human ingenuity, a testament to our enduring desire to overcome the inevitable decay of time. The quiet hum of this machine, even in stillness, speaks to a fundamental drive within us, a desire to preserve, to protect, to hold back the relentless tide of entropy, one carefully cooled molecule at a time. The kitchen is quiet, lit by the soft glow of the under-cabinet lights. A stainless steel refrigerator hums, a low, constant thrum that blends with the barely audible ticking of the clock. It is a familiar sound, so pervasive we rarely notice it, a mechanical heartbeat in the center of daily life. Inside, a constellation of containers holds the remnants of meals, the promise of breakfasts, the careful curation of a week's worth of sustenance. And that, perhaps, is the quiet miracle of it all, the slowing of time itself. John B. Gorrie, born on October 3, 1803, on the island of Nevis in the Leeward Islands, wasn't thinking about miracles when he first began to experiment. He was a medical doctor, trained at the College of Physicians and Surgeons of the Western District of New York, and his concern was yellow fever. He spent his childhood in South Carolina and later moved to Apalachicola, Florida in 1833, a port city on the Gulf Coast, where the heat and humidity were relentless. Apalachicola was a place of bustling commerce, but also of frequent epidemics, and Gorrie saw firsthand the suffering caused by the disease. His research, fueled by a desire to alleviate the fever's symptoms, led him down a path that would ultimately change how we interact with the very building blocks of life, preservation. He wasn't trying to create cold for the sake of cold, but to create a better environment for recovery. The prevailing theory at the time, and one that Gorrie embraced, was that yellow fever was linked to bad air, miasma, and that cooling the air could reduce its potency. He believed that a chilled environment would strengthen patients and allow them to fight off the illness. The idea wasn't entirely new. People had used ice for centuries, but ice was a fleeting resource, expensive to harvest and transport. Gorrie envisioned a mechanical solution, a way to generate coolness on demand. He was a man of many roles in his community, a resident physician at 2 hospitals, a council member, a postmaster, even president of the Bank of Pensacola's Apalachicola branch. He was also a founding vestryman of Trinity Episcopal Church and a secretary of his Masonic lodge. This suggests a man deeply embedded in the fabric of his time, a pillar of society, not a solitary inventor cloistered away in a workshop. He was driven by practical concerns, a desire to serve his fellow citizens. His early experiments were crude, involving the use of hand-cranked pumps to create a vacuum and evaporate ether. The ether absorbed heat as it changed from liquid to gas, and the resulting cooling effect was used to lower the temperature of the air surrounding the patient. It was a cumbersome process, and the machines were far from reliable, but it was a start. The machines were not about making ice, but about creating a flow of cool air, a deliberate resistance to the natural warmth. The physics at play, of course, was simple enough, though not fully understood at the time. Evaporation requires energy, and that energy comes from the surrounding environment. As the ether vaporized, it drew heat from the air, lowering its temperature. The challenge was to make the process efficient and sustainable. Gorrie continued to refine his designs, experimenting with different refrigerants and pump configurations. He wasn't merely building a machine, he was attempting to harness a fundamental principle of thermodynamics. The story of Gorrie is often framed as a tale of innovation, stifled by lack of funding and recognition. He spent years seeking investors, but his ideas were met with skepticism and indifference. He patented his machine in 1851, but it failed to gain widespread acceptance. He envisioned using his technology to create a more comfortable environment for ships and hospitals, to preserve food and medicine, to improve the quality of life for people around the world. But his vision was ahead of its time, and the technology was simply too expensive and unreliable to compete with traditional methods. It's easy to imagine him in his workshop, surrounded by copper pipes and glass condensers, driven by a relentless pursuit of a seemingly impossible goal. He wasn't a trained engineer, but a doctor with a practical problem and a deep curiosity. He was a man of his time, deeply influenced by the prevailing scientific theories and the social concerns of his day. He was a builder, a tinkerer, a man who believed in the power of human ingenuity to overcome even the most daunting challenges. The surprising thing is that Gorrie's work wasn't immediately forgotten. After his death in 1855, his designs were further developed by others, notably Ferdinand Carré, a French engineer who created a more efficient absorption refrigeration machine in 1859. Carré's machine used ammonia as a refrigerant, and it was widely adopted in breweries and meatpacking plants. This is where the story begins to truly shift, from a medical curiosity to an industrial necessity. The demand for preserved food and beverages grew rapidly in the late 19th century, and Carré's machine provided a solution. The idea of cooling as a deliberate act, a way to slow down decay, began to take hold. What this means is that the refrigerator isn't simply a device for keeping food cold. It's a physical manifestation of our desire to control the natural world, to resist the relentless tide of entropy. The second law of thermodynamics tells us that entropy always increases in a closed system, that things tend towards disorder and decay. But the refrigerator is an attempt to create a local pocket of order, a temporary reprieve from the inevitable. It's a machine that fights against the natural flow of time, preserving food and extending its shelf life. The kitchen is a strange sort of laboratory, isn't it? A place where we manipulate the building blocks of life, transforming raw ingredients into nourishing meals. And the refrigerator is the central piece of equipment in this laboratory, the guardian of our sustenance. It's a testament to human ingenuity, a symbol of our ambition to overcome even the most fundamental laws of physics. The electric motor, a later innovation, made refrigeration accessible to the masses. Before the advent of electricity, refrigeration was limited to large-scale industrial operations. But with the development of reliable electric motors, it became possible to create small, self-contained refrigerators for use in homes and businesses. This is where the modern refrigerator begins to take shape, the appliance we know and rely on today. The compressor, the condenser, the evaporator, these are the key components of the vapor compression cycle, the technology that powers most refrigerators. The refrigerant circulates through a closed loop, absorbing heat from inside the refrigerator and releasing it into the surrounding environment. The flow of heat, of course, is not a one-way street. The refrigerator doesn't create cold, it moves heat. It's a subtle but important distinction. The heat that is removed from inside the refrigerator is simply transferred to the outside, warming the kitchen air. The refrigerator is not a source of energy. It's a conduit, a facilitator of heat transfer. The materials themselves are crucial. Copper, with its excellent thermal conductivity, is used for the coils and tubing. Insulation, typically made of foam, prevents heat from leaking back into the refrigerator. The refrigerant, a carefully chosen chemical compound, is the key to the entire process. The choice of refrigerant has evolved over time, driven by concerns about safety and environmental impact. Early refrigerants, such as ammonia and sulfur dioxide, were toxic and corrosive. Later refrigerants, such as Freon, were more stable and less harmful, but they were found to deplete the ozone layer. Today, researchers are developing new refrigerants that are both safe and environmentally friendly. The refrigerator is a complex system, a delicate balance of physics, chemistry, and engineering. It's a machine that relies on precise control and careful calibration. A small leak in the refrigerant line, a faulty compressor, or a malfunctioning thermostat can disrupt the entire process, causing the refrigerator to fail. The hum of the motor is a constant reminder of this delicate balance, a subtle warning that things could easily go wrong. Consider the sheer scale of this technology. Millions of refrigerators operate around the world, preserving food and extending its shelf life. This has a profound impact on our food supply, reducing waste and making it possible to transport food over long distances. It has also changed our eating habits, allowing us to consume a wider variety of foods and to eat year-round, regardless of the season. The refrigerator is not simply a household appliance. It's a fundamental component of our modern food system. And yet, the very act of preservation raises a deeper question. What are we preserving, and at what cost? The refrigerator allows us to store food for longer periods of time, but it also alters its nutritional value and its taste. The process of refrigeration slows down the natural decay of food, but it doesn't stop it entirely. The food continues to change, albeit at a slower rate. The question of optimal preservation, of finding the balance between extending shelf life and maintaining quality, remains a challenge. The kitchen air is cool, a gentle breeze emanating from the open refrigerator door. The scent of fresh produce mingles with the metallic tang of stainless steel. The containers hold a kaleidoscope of colors and textures, a testament to the abundance of our modern food supply. The hum of the motor is a constant presence, a subtle reminder of the delicate balance that sustains this abundance. The refrigerator is, at its core, a testament to our ability to manipulate the environment, to create pockets of order in a chaotic world. It is a machine that fights against the relentless tide of entropy, preserving food and extending its shelf life. But it is also a reminder of the fragility of this balance, the delicate interplay of physics, chemistry, and engineering that sustains this abundance. The quiet hum of preservation is a constant invitation to consider the consequences of our actions, the subtle trade-offs that we make in our pursuit of comfort and convenience. The temperature within these walls is carefully maintained, a constant, deliberate resistance to the natural world, and the food within remains for a time suspended in its own moment. The vapor compression machine hummed, ether turning to ice in a sealed chamber. Evans' invention cooled rooms, not just food. The cold spread slowly, steady, through metal pipes and stone walls. The world held its breath as pressure did its work. Thermodynamics ruled the scene, cold bending heat's will. The open boat's men fought the sea, but here the cold fought back. A vacuum pulled ether into vapor, a whisper of power. The temperature dropped, steady as a heartbeat. The cold moved, but not without purpose. It settled into the walls, the air, the stillness between the sounds. The machine's rhythm slowed, then stopped. A final breath of cold lingered. The air grew still. The ether lay quiet. The cold stayed.